Hello. In today's video, I want to talk about kind of a rough draft that I'm working on for a bus controller for the 8086, and in this case, a V30. And what I mean by a rough draft is I'm basically creating my own bus controller using a V40. The reason for this is the bus controllers of this era, they're very hard to come by at a large quantity. I'm sure I could find a one-off here or there, but any quantity that could be done, like on a production scale of making 10 or 15 boards, say. So the V40 is obviously not the best choice. This one does run at 20 megahertz, so it is running quite fast as far as an 8088 goes, but it's definitely not fast enough to run the 8086, the V30, at say 5 megahertz. Um, Anyway, I'm going to explain how this is kind of wired up and give a little demo. What I've done is on the V40, if you can see here, turn that up, you can see I've got just the processor and ROM. I've got my latches and my decoding over there. Now, not to get too sidetracked, but the reason for only ROM is I need to reduce the number of clicks per command given to the 8086. The more it spends over here processing, the slower it runs your PC. So if there's RAM on there and you do a bunch of calls or pushes or pops or whatever into ROM or RAM, you're going to be wasting time. And this is entirely about timing. And it's not that it has to be exactly in time, like in precision, but when you waste time, it goes slower, is what it comes down to. So, anyway, this first row here is three latches, a transceiver, so latch, transceiver, latch, and latch. And I've got some decoding here. Um, all I/O read writes here, and what they do is it works on kind of the principle of my Raspberry Pi board, as in it toggles the clock on the V30 and reads, in this case, the status S0 through S2 in and determines which bus cycle needs to be done. And obviously, if there's no bus cycle needed, it skips and toggles again. Hooked up to the reset and the address latch here to the 1, 2, 3 latches for the address off the V30. So you can kind of divide this board, those two, and then these four belong to the V40. Everything this side plus this chip belong to the V30. So the V30, you can see, does not have its own clock. It's driven by the V40, and that's why the timing is so necessary. As I mentioned, this is running in maximum mode. Minimum mode would work fine, just a little bit different on the decoding, different lines. But I went with maximum mode for the main reason that that's what all the following chips use, like the 286 and the 386. They don't have a minimum mode, maximum mode. It's the status lines that you're decoding. I kind of want to work this maybe to make like a 286 one day. So I want to make sure I know it'll work at minimum mode because I do that with the Raspberry Pi. I want to make sure it works in maximum mode here. And then also, this would extend to the function of the 8087 as well. So basically, you got your latches for your V30 here. So I've got A0 through 7, A8 through 15, and then I added this later. I would start with just a 16-bit system. So over here, I've got the remaining 16 through 19 address lines. Bank high enable goes over here to the input, along with A0 to the input, so it can be decoded, whether it's a 16-bit read or an 8-bit odd or even read. So that can all be decoded. And then off of here, you have the data transceiver. So you have just 3 chips involved for that right now. right here, this is a transceiver, and this is for the output off the low side, the data 0 through 7, but it's only an out. Um, there's a reason for this. So I have a latch here for the in, and this is so that you can latch off of an 8-bit data, the first byte, and then the second byte, the odd byte, comes through just a transceiver here. Very much like how the early 286s would work. So you don't need to latch the second byte. So it requires right off the bat 3 chips for your data for your data bus, not just 2. But we're missing one more transceiver for a 16-bit system. So this is the high side crossing over to low, but you're going to also need one more transceiver for the high side, the odd side to odd side. This is set up as a 8-bit system only right now. I put in the interrupt controller here and the system timer here. So this would match my motherboard project, and I should be able to connect in. So I haven't done it yet, but I've got these pin headers on a motherboard and a whole handful of wires, and plugging them into the correct location. So the address bus here, the 8-bit data bus here, interrupts here, and then your IO read write, memory write is all up in here off of this latch. And that should plug into the board. The only thing is, at this scale, you start to run in at that many wires, the stability just starts to fall apart. So I haven't quite got that far. Plus, I haven't wrote the code entirely to handle full operation yet. It's not overly difficult, but I haven't done that yet. It's kind of I'm trying to decide on finishing the code. I also need to include the 16-bit side of things. So I also need the IOMEM 16 off the ISA bus input as well. So you have several different bus cycles that have to be accounted for during the control. So anyway, what it really comes down to is this is just the prototype, kind of a proof of concept. This obviously needs to be reduced, just reduced in size to a smaller board, but should be changed out for something much quicker. Now, if I want to stay with the x86 family, they do make 188s that run at 40 megahertz, and that might put us at the range we need to be. But there's other microcontrollers out there on the market that could stand in for this. I just need to have the appropriate number of IOs for interpreting the bus. So I'm going to turn it on here, kind of a little demo. So what we're looking at here is address 15, 14, 13, and 12. This is my data bus put in here, and it's got the value of 90 on these resistors as the default value. And as you can see, it's only 8-bit, but it's feeding into both the low data and the high data lines. Just proves that it works. So every time this counts up, because this is address 15 here, that's 64K worth of bus cycles, not megahertz. There's 4 clicks in a bus cycle. So I've timed it out, not on this particular build, but other builds. It's decent, but you're not even in the megahertz range for the most part. And the more I have to develop the code, the slower this is going to get, because it's going to require more clock cycles to interpret all of this. So anyway, thanks for checking in on the project today, and catch you on the next video. Thanks.